participants. So welcome back to the post-lunch session of the refresher course. So it is pleasure to have Professor Shamik Ghosh, who's a professor of mathematics at Jadavpur University, Kolkata, West Bengal. His main research interests lie in the area of graph theory and abstract algebra, and he has worked on a wide range of topic in graph theory, more specifically I think algebraic graph theory. And I must particularly mention his paper on power graph of groups, since this topic has been introduced to the participants in this course. So this paper with Peter Cameron, I think were some of the early papers to have been written on this subject, and is being widely referred to in the literature. So thank you, Professor Ghosh, for accepting our invitation and for delivering a talk in this workshop. So Professor Ghosh will talk on intersection graphs of ideals of rings. Okay, so over to you, Professor Ghosh.
Yeah, thank you very much, Dr. Kadu. And I am also thankful to Professor Binayak Joshi, who invited me first in this workshop. I am really very much pleased to say something about this work. This is a part of algebraic graph theory, and I am also indebted for this work to my student, Dr. Ivy Chakraborty. It is the beginning of this work is with her. It was with her PhD work, and later on with Professor Joseph Burgess of Christ University. She wrote a very good survey paper of these intersection graphs of ideals of rings. Now, the thing is that the motivation of the studying these intersection graphs of ideals of rings, that the story starts like this. Can you see the presentation? I switched the paper.
Yes, we can see your presentation. So you have a slide on intersection graph now.
Yeah. Okay. I am asking because there were a lot of technical problems before. However, so story begins like this, that it is the intersection graph is defined as follows. Suppose you have a arbitrary family of sets, any collection of sets, and mind it here, the collection in this collection may be the same set you are taking multiple times, it may happen. So you have just a collection of sets, and you declare all these sets as your vertex set of a graph, and two such vertices, that is two such sets, are adjacent. If they are unequal means they are not same. By set they may be equal, but they are not same, that we mean here. And just to avoid the loops on the graphs, and we want to make it a simple graph, and their intersection is non-empty. So it is the basic idea of intersection graph, that given any collection of sets, the vertex set is that collection of sets, and two such vertices are adjacent if and only if their intersection is non-empty. So if we make them a simple undirected graph, and then we may ask that what is the set of or class of graphs that we can incorporate with these intersection graphs, and the answer is that it incorporates universe, that is all. That is, every simple undirected graph is an intersection graph. So the proof, let us see the proof of this result. The proof is very simple, that suppose you start with a simple undirected graph, and you collect all the maximal clicks of the graph G. Now, suppose this collection, as I have written here, script C, that is the collection of C alpha, where alpha belongs to lambda. And for each such vertex of the graph, each x belongs to V. Suppose we define a set Sx such that it is the collection of all alpha such that x belongs to C alpha. That is, you can say that it is basically the collection of all the maximal clicks in which the particular vertex x is belonging to. And then you can see it sets up a bijection between the set of vertices and this collection of Sx. Now, if we consider the intersection graph of Sx, of this collection Sx, you will see it is the same as the graph G, because you know that two vertices x and y, if we pick up from the vertex set of G, if they are adjacent, then they are joined by an edge, and that edge must belong to a click, a maximal click. And so they must belong to a maximal click of G, and that means Sx and Sy must have the non-empty intersection. They must have a common member, and so they have the non-empty intersection. And so you have that because of the what I should say, the adjacency relation of the intersection graph. This Sx is adjacent to Sy, right? And so the whole graph is isomorphic to the intersection graph of this collection of sets. So as I told you that it is the result that every simple undirected graph is the intersection graph. So one may think that it is not so much interesting because we get that every graph becomes a class of belonging to the class of this graph. So people try various ways to define intersection graph in some particular cases, in some particular varieties. And some of them went for the geometric pattern, that intersection of triangles, intersection of lines, parallelograms, trapeziums, spheres, and made boxes, cubes in other ways. And there are various branches of graph theory like boxicity, cubicity, disk graph, and many other graph, this parallelogram graph, trapezium graph, permutation graph. These came into the picture of the geometric point of view, and another class of people, rather another set of people, tried to do this for some algebraic structure. They tried to get the graph from the algebraic structures, semigroups, groups, rings, and many other algebraic structures tried to form these graphs. The graphs forming from the poset is very known. In fact, you can easily correlate a directed graph with poset as a binary relation. And so this was an age-old practice to relate the posets of the partially ordered sets with the directed graph. And in the case of the symmetric, some binary relation with the undirected graph, and the binary matrices related with this undirected graph, and any matrix with the directed graph. So these were known, but from the algebraic structure like semigroup, group, ring, fields, vector spaces that evolved the various kind of graph structure, that was new in the mid-60s. And Bozak in the 1964, he took the first step and he started with a minimum algebraic structure that is a semigroup. He collects the set of all proper subsemigroups of S and considered that that is the vertex set, and two such subsemigroups, they will be adjacent if and only they are unequal and their intersection is non-empty. That is basically Bozak was studying the intersection graph of the collection of all proper subsemigroups of S, right? Now he proved that he first attacked the connectedness problem of this graph, and he proved that if the whole semigroup is uncountable or a periodic with more than two elements, then the graph is connected. So that was the first result that the Bozak. That was the first result that Bozak obtained. And then this study was carried over for the groups for more beautiful or rich structural things that we will get in the groups. So total results is carried over to the groups, and then the collection was taken as a subgroup of the group. But you can understand it is not merely the intersection graph of subgroups will work, because all subgroups have the common element, that is the identity element of the group. So if I say that two subgroups are adjacent if and only if they have non-empty intersection, that becomes meaningless, because that gives you always a complete graph, because all of them has a non-empty intersection. So what Cezanne and Pollock did, they just slightly modified the definition, and they said that two vertices are joined by an edge if and only if their corresponding subgroups have a non-trivial intersection. That means the intersection contains more than one element, not only the singleton identity. And Zelinka later on continued the study in case of finite abelian group. And that study of Cezanne, Pollock, or Zelinka, that was the basically starting point or the motivating point of defining these intersection graphs of ideals of rings. So it was then the completely new structure, that it is the motivation came from already the group theory. It take a group, take the collection of subgroup, and take the non-trivial intersection to make the adjacency. So likewise, you can start with a ring, and you can start with all the some ideals of the ring. Now for general definition, we are taking the left ideals of a ring. You can take for commutative rings, you can take two-sided ideal. Also for non-commutative ring, you can take collection as two-sided ideal, and instead of left ideal, you can take right ideal. However, so I am just speaking, just considering the left ideals. So suppose you start with a ring, and your collection is the set of non-zero proper left ideals, and then your graph that you are constructing, the vertex set, is the collection of non-zero proper left ideals, and two such vertices, or that two such ideals, are adjacent if and only if their intersection is non-zero, not non-empty, non-zero, and they are unequal. So this we call the intersection graphs of ideals of ring. Now here you can see that there is an example for the ring Z12, and that is integer modulo 12, ring of integers modulo 12. Now you see that how many ideals are there. So you know that these are principal ideal rings. So these are the principal ideals. So the ideals are generated by the factors of 12. Obviously, the 1 or 12 is not here, because 1 will generate the whole ring and 12 is generating the zero ideal, but we are taking the non-zero proper ideals. So you see that there are 4 such ideals generated by 2, 3, 4, and 6. I am avoiding the writing the bar over 2, 4, 3, 6 just to avoid complication in writing, nothing else. So actually, it should be strictly written as the bar on them. However, so I think you can easily understand it. So you see that the intersection between the ideal generated by 2 and the ideal generated by 4 is basically the ideal generated by 4, because 2 generated the elements 2, 4, 6, 8, 10, and 0, that is 12. And 4 generates that 4, 8, and 12, that is 0, and that is a subset of the ideal generated by 2. So their intersection is non-zero. So you see they are joined by an edge. And similarly, you see that 2 and 3 are joined by an edge, because their intersection is basically the ideal generated by 6. But you see that the ideal generated by 3 is not adjacent to the ideal generated by 4, because their intersection will give you only the zero element. The ideal generated by 4 has elements 4, 8, and 0, and ideal generated by 3 has elements 3, 6, 9, and 0. So only common element is 0, and that is why there is no edge between them.
No,
so in this way,
sorry to interrupt you. I think ideal generated by 3 and 4, there will be an intersection, right? I mean, 12 is in the intersection.
that is a zero ideal.
No, non-trivial intersection.
Non-trivial intersection is expected.
Non-trivial.
No, 3 and so 3 and 4. So 12 element 12 is in both, right?
12 element
Oh,
is
so
zero.
okay,
Yeah,
okay.
12
You are looking
element
at
Here we
is
consider
okay, fine, fine, fine. So
Z12.
fine, fine, fine. Yeah.
the element 12 is zero here, and you've seen the definition that we say that's a non-zero intersection, right? So when we get a similar case that happened for 4 and 6, you see that 6 generates 0 and 6 only, and 4 generates 0, 4, 8. So only intersection is 0, right? So these are not adjacent. So in this way, we are forming the graphs that which have the non-zero intersection. We are joining by the edge. That 2 and 3 has the non-zero intersection. 2 and 6 have the non-zero intersection. 3 and 6 have the non-zero intersection. So they have the edge. So typically, it is a graph that is forming by the ideals of the rings, right? So similarly, you can see the other examples. The above is for Z30, and you see that these are the factors, the 2, 3, 5, 6, 10, 15. And similarly, you see that in between 2 and 15, only 0 is the common, and that is why there is no edge between them. But the ideal 6 is contained in the ideal generated by 2, and that is they have the non-zero intersection. Similarly, 2 and 3 have non-zero intersection, so they are having the edge. Sorry. Now this is the graph of Z30. Now look at the graph of Z32. And here there are 4 vertices, and each 2 of them are adjacent by an edge. That is, this is a complete graph K4. You see that is the complete graph of 4 vertices, because you see that between any 2 of them, actually one is contained in the other. Therefore, for every ideal 2, 4, 8, 16, the intersection is non-empty, and that is why it gives you a complete graph. So in this way, we have seen that various kinds of graphs we are getting from the ideals of rings. But naturally, following the Bozak and many others, whenever we construct a new graph class, so we are very keen to know that when they are connected first. And that is why we also studied the connectedness of the graphs of ideals of rings. And sorry. So we started with the connected of the graph Zn in particular. And our result is that it is connected for very only for a single kind of graph, single class of graph, which is where n is just the product of 2 primes. It is the graph just 2 vertices, and there is no edge between them. So it is a null graph containing 2 vertices and no edge between them, and it is the only disconnected graph among the graphs of Zn. The proof is going as follows, that first of all, you can see that if the graph is the product of 2 primes, then it has only 2 non-trivial ideals, P and Q, and their intersection is the ideal generated by PQ, that is the 0 ideal, so there is no edge between them. And so the graph is disconnected, that is 2 isolated vertices that the vertices are there. So the graph is disconnected. The converse part requires more. Actually, if we consider the graph is disconnected, so suppose you consider that n is the product of k primes, right? And these primes may not be all distinct. So first we want to show that whenever k is greater than equal to 3, you see that always the graph is connected. So suppose we consider the I is generated by one single prime, that is P1, and sorry, J is generated by another non-trivial ideal. So suppose generated by M, where M divides N, right? Now you see that if P1 divides M, then the whole ideal J is contained in I. I is generated by P1, and if M is a multiple of P1, then M itself contained in the ideal generated by P1 as a multiple of P1. And so here you get that J is contained in I, and so their intersection is J, that is non-zero, and so they are adjacent. And then we go for the next case where P1 does not divide M. Just 1 second, excuse me, have a water. Sorry. So in this case, that you see that if we consider that any prime factor of M, and since P1 does not divide M here and P1 is a prime, so P1 does not divide any factor of M. So their GCD is 1, and so you get that the ideal, suppose we consider the ideal generated by Q, and naturally since number of primes here, that is K is greater than or equal to 3, so the product of 2 primes cannot be equal to N, so it is less than N, so the ideal K is non-trivial. That so, and we have that their intersection is non-zero because their intersection is generated by P1Q, and you see that P1Q is not equal to N, so it is not 0. So I is adjacent to K. And similarly, since Q is a factor of M, so certainly the M bar is belonging to the ideal generated by Q. It should be written as Q bar, as I say, that I avoided the bar on the brackets. So M bar is belonging to Q bar, and so you have that their intersection is also non-zero. So our ideal that is generated by P1, it is adjacent to J as well as adjacent to K, right? So J, this ideal I is adjacent to K, and ideal J is adjacent to K. So ideal I is connected with J through K. I to J, there is a edge. J to K, there is an edge. So I to J, there is a path through K. And so we get that every other ideal other than I, they are adjacent to I. So if we consider any 2 ideals, or that is any 2 vertices, so both of them are connected to I. And so you get that the whole graph is connected because then any 2 vertices are connected. And in this way, you get that any graph where a number of primes in the factor of n is greater than or equal to 3, they are connected. So only 2 things are remain. So either it is p square, n is p square, or pq. So it is not p square because p square contains only one single non-trivial non-zero ideal, and that is only generated by p. So it is a single vertex graph, and that is we consider connected in the graph theory. And so it must be pq, where P and Q are 2 distinct primes. And so that is the proof that we got, that the graph of Zn is disconnected if and only n is equal to pq, where P and Q are distinct primes. But here you see that you can see along the proof is saying actually much more about the graphs of Zn. Actually, you see that from the ideal I, the distance of any other ideal J is at most 2. In the case 1, it is adjacent, and in the case 2, it is the distance is 2 because IK was adjacent and KJ was adjacent. So you see that from any ideal J to I, the distance is 2. And so between any 2 vertices, the maximum distance can be 2 plus 2, 4, if it is through I in the worst case. So you can see that the graph is of small diameter, and so you can see the graph is dense. So in our graph theory, 2 terms are very popular, dense and sparse. We say the graph is dense if there are more edges, many more edges, large number of edges. You know that in a simple graph, the maximum number of edges can be n choose 2, n into n minus 1 by 2. And the minimum number of edges is certainly 0. So the graph like a path, you see a path where the number of edges is actually the number of vertex minus 1. This kind of graph has very small number of edges because they are in the order of n. That is the number of vertices. But if you have some, say, n square by 2 edges, or say n square by 4 edges, where n is very large, then you see that there are a large number of edges, and the distance between two vertices are small means there are a lot of edges in the graph. As we will explore the graph, you will see also that most of all the graphs are non-planar, most of all the graphs are Hamiltonian here. So these graphs are very dense graphs, the graphs of Zn. Now moving from the general ring, from the particular ring Zn to the general ring, we can study when the graph is connected or not, but that requires some more ring theory here. We say that one ideal is minimal if the ideal I, and in between the ideal I and the zero ideal, there is no ideal other than 0 and I. So then we say the ideal is minimal, and an ideal is, say, maximal if between that ideal and the whole ring R there is no such ideal. So we say that the ideal is maximal. Here for the maximal I should write the proper ideal also. That is missing here. However, it means that a non-zero proper ideal is called maximal ideal. So these are the minimal and maximal definition. Now, suppose we consider the product of Z2 and Z3. So you know that here in Z2, 1 plus 1 is 0, and in Z3, 1 plus 1 plus 1 is 0, right? So you can generate only two kinds of ideals here, that is non-zero proper ideals here. One is consisting of 3 elements, 0, 0, 0, 1, and 0, 2. And another is consisting of 2 elements, that is 0, 0, and 1, 0, right? So these two ideals, you see the only common element is 0. So these two ideals are minimal ideals. There is nothing in between the 0 ideal and them. So both these ideals are minimal ideals. So all the ideals, all the non-trivial ideals of this ring are minimal ideals. So that is basically the theorem. You see that the intersection graphs of a ring, this is for any arbitrary ring, the result is true, that it is disconnected if and only the ring contains at least 2 minimal left ideals and every non-trivial left ideals of R is minimal. And in fact, here you can see that they are maximal also. If all of them are minimal, then they are maximal also. And so you see that basically it is a very trivial case, the disconnected case. So almost all graphs, intersection graphs of ideals of rings are basically connected, because you see that only the null graphs, you are finding only the null graphs for the disconnected case. Otherwise, all graphs are connected. Now, in particular, if you consider the theorem becomes more beautiful, nice, or rich when you consider the commutative ring with identity, and then you have a very categorical answer that the graph is disconnected if and only it is a direct product of two fields. So accepting the direct product of two fields, no graphs are disconnected, so every other graphs are connected. That is the result says. Now from the connectedness, we shift to the studying the completeness of the graph, that when the graphs are complete, and as I have shown to you, there is another example, another two examples. You see that one is of Z32, which is complete, the complete 4-vertex graph with 4 vertices. Each of them are adjacent with each other. But the graph of Z36, you see, there are a lot of vertices, but you see that between 12 and 18, there is no edge. 9 to 12, there is no edge. 4 and 9, there is no edge, and so on. So this graph is not complete. Now, for Zn, the answer is very simple, that the graph becomes complete if it is only the power of a single prime. Then it becomes complete, and that is the if and only if result. And as you have seen that for the graph Z32, and all the ideals are just multiple of 2 and powers of 2, 2, 4, 8, 16, 32, and one is contained to the other. And so any two vertices, the intersection is the smaller one, and that is why all of them are adjacent. So this is the necessary part, that why n equal to p to the power m is complete. But one can again prove the sufficient part also, that you can assume the graph is complete, and then you can prove that if there are other primes, at least you will get two vertices which are not adjacent. And so you can prove that the graph is complete, if and only if it is power of a single prime. Next, very interesting theorem is that every integral domain gives you a complete graph, but which is not a field. Which is not a field means actually if you consider a field, so we cannot construct the intersection graphs, because then the vertex set will be void, because in the field you have no non-zero non-trivial ideal, only the zero ideal, and the whole field is the ideal, are the ideals. So there is no non-zero proper ideal, and that is why you do not get vertex set non-empty, that becomes empty. So integral domains are complete graphs, which are not fields. And so in particular, the most popular ring in the commutative ring theory, all the domains, is the example that is the ring of all integers. And it is a complete graph as per this theorem. And but you notice that there are non-integral domains also which are complete, that is Z p to the power m's are complete. Now,
Excuse me, sir.
yeah,
Excuse me. Can I ask a question?
obviously. Yes, yes, please.
The last slide. In the statement, it is the integral domain, which is not a field.
Yeah.
Can we replace it by infinite integral domain? The graph of an integral domain.
Z is the infinite integral domain.
So we can replace that by infinite integral domain.
No, not replace. This is an example. Z is an example of an integral domain, which is not a field.
Okay.
What is an integral domain? An integral domain is a commutative ring with identity where product up to non-zero element is always non-zero, right?
Okay.
But in field structure, you get multiplicative inverse for every non-zero element.
Non-zero element.
Like
Right.
rationals, if we consider all the rational numbers, so you get the multiplicative inverse for all the non-zero elements. But if we consider the ring of integers only, then accepting 1 and -1, no elements are multiplicatively invertible. 2, 3, all these are not multiplicatively invertible.
Not in.
Right. But product of this property retains, the product of two non-zero element is always non-zero. Or in the other way to say, if the product of two element is 0, then one of them must be non-zero. One of them must be 0, right? So
but every finite integral domain is filled. I think Pradeep sir asking regarding this.
Yes, every finite integral domain is a field.
Yes.
Right. Every finite integral domain is a field. Here you see that if you consider ZP, right? But then ZP has a void graph, empty graph, because the only ideal that is generated by 0, that is the same as the and the ideal is generated that's the whole ring generated by 1. So there is no non-zero proper ideal in ZP. ZP is a field with a finite integral domain, but there is no non-zero proper ideal, right? And that is why we are just not consider this ring in our discussion, because then the vertex set become empty. Actually, in the graph theory, we can assume that, or we can allow that the H set may be empty, and that we call the null graph. But generally, we do not allow the vertex set is empty, because if the vertex set is void, and like the language of Hardstyle, that whole the discussion is void as well. So we have nothing to discuss about it, right? So field we are not getting here because of this, because we do not get the non-zero proper idea. But here, all the other integral domains, and that is not a field, and certainly they must be infinite, as somebody told here that the result is known to you that any finite integral domain is a field. So whenever you get an integral domain is not a field, that must be infinite, right? So you see that Z is a field, an integral domain which is not a field. If you take the polynomial ring over Z, then that is another integral domain which is not a field. So you can find that various integral domains which are not field. For example, if we collect that, suppose Z root 2, that is set of all A plus B root 2, where A and B are integers only, that is not a field. So there are a lot of infinite integral domains which are not a field, but all of them have the complete graph of intersection graphs of ideals of them, right? So, but here we are showing that not only integral domain, there are other commutative rings which have finite characteristic. Integral domain, you know that here you have only the infinite integral domain we are getting here. But here the finite integral domain, finite commutative ring, which is not an integral domain, but its graph is also complete. So this is only sufficient condition. That is not a necessary condition. That is in the note that we have noted here, right?
Yeah. Okay.
So we pass on to the another class of ring to study the completeness. And actually, what you are seeing that in the case of Z32, that all the ideals are being, one is subset to the other, another is subset to the other, like this. So when this thing happens, that suppose you get a sequence of ideals, and one contains the next, the second contains the third contains the fourth, and if every such chain, that we say some descending chain, so in every such descending chain, if it terminates after some finite terms, then we say the ring is the Artinian ring. So if we do it for left ideals, we say it's a left Artinian ring. So suppose we consider a left Artinian ring, and then the result you can see that the left Artinian ring, its graph is complete if and only if R has the unique minimal left ideal. So in the connectedness, you can remember the result. It was the result that all the ideals are minimal left ideals. But here we say that there is unique minimal left ideal, and then the graph is complete, and that is the necessary and sufficient result for particularly left Artinian rings. So in this way, we can study connectedness and completeness, both for Zn in particular and for some arbitrary ring or some ring with particular properties like this Artinian property and others. And similarly, this is another property. This is for, in particular, commutative ring with identity. And there is a definition needed here. That is, an ideal is called decomposable if it can be splitting into two ideals, and their addition is our given ideal, but their intersection is the zero ideal. Then we say that the ideal is decomposable by the ideals J and K. But here you have that for commutative ring with identity, our result is that the graph is complete if and only if every non-zero ideal of R is indecomposable. That is, there is no such ideal which is decomposable into two or more ideals. So this is for any commutative ring with identity. These four conditions are actually equivalent, and by using any of them condition, you can check that whether the graph is complete or not. It gives you a complete description of when the graph of these ideals are for commutative ring with identity in general, for any commutative ring with identity, it is complete or not. So this is the general study of the graphs of general rings. And now we pass for the last result in the completeness properties. And this result was very challenging, and this is a hard result. This is you know, some famous results are there that for any unique factorization domain, Gauss theorem says that its polynomial ring is also unique factorization domain. Like Z is UFD, and so ZX is also UFD, like that. And also you can remember Hilbert basis theorem, where that polynomial ring over Noetherian rings are also Noetherian. And that proof is also non-trivial and very interesting result that is known as the Hilbert basis theorem. And like this, you can achieve a very nice result here, that if for a commutative ring with identity, if its graph is complete, if and only its graph of its polynomial ring is also complete. So here one part is short, obviously. If the bigger one, that is polynomial ring, is complete, then the G of R is also complete as a subgraph of this, and as an induced subgraph of this, so it becomes complete. But the other part, that is from R is GR is complete, to prove that GRX is complete, it requires some results, and one of these lemma here. So, but I am not describing here in details, that is a long proof. But it gives us a beautiful result that the graph of commutative ring with identity is complete if and only if the graph of its polynomial ring is complete. So with this, we leave the completeness part of this study, and then we come for the cycle structure of the graph. And we see here that it contains a cycle of length 3, in particular in the case of Zn, if n is the form that prime to the power 4 or p square q or pqr. And then next result, we see that actually it has a cycle if it n is a multiple of p to the power 4 p square q or pqr. So we can conclude as a corollary that it does not contain a cycle in some very typical cases where n is p square or pq or pq. P square means a single point graph, pq means two isolated point graph, pq means just an edge. P and p square are the only non-zero non-trivial ideals here. So accepting these graphs, all graphs contains a cycle of length 3. So again, you see that graph is dense, and most of all the graphs are dense, and most of all the graphs contains cycles, right? And then from this idea, we go for planarity. And first thing that we discover that the graphs which are non-planar, the first graphs which are non-planar, these are coming by the product of 4 primes. Either it is of the form PQQ, P square Q square, P square QR or PQRS, but not P to the power 4. P to the power 4 is just a triangle. Here the non-zero, non-trivial ideals are only P, P square and PQ, which is just triangle. So it is planar. So accepting all the primes are same, if all these are product of 4 primes, at least 2 are distinct, and then we see that graphs are non-planar. The proof is very simple, because in the left graph, you are seeing that subgraphs that isomorphic to K5, and this is for all the first 3 cases, PQQ, P square Q square, and P square QR. You see that the graphs generated by the ideals P, Q, P square Q, and PQ, they are forming a clique of 5 vertices. That is a complete graph of 5 vertices, and that we know that is a non-planar part of the graph, and so the whole graph is non-planar. And for G, PQRS, if you consider the graph G, PQR, PQ and QR, and they are then forming the K5 induced subgraph, and so the graphs are non-planar. So any graph which are multiple of them are non-planar. So only the remaining part is that either it is P square, PQ, P4, P5. P5 is just K4, that 4 vertices, P square, P cube, and P4. All of them are adjacent to each other. This is K4, and PQ, 2 vertex null graph, and P square Q and PQR. This is the graph of PQR. P square Q, we can remember the graph of Z12, that is a triangle and with an antenna-like thing. And these are only the planar graphs. All other graphs are non-planar. So you see again the graph class is dense. So these are only the planar graphs that you can characterize for the graphs of Zn. Now we go for the deeper structure of the graphs of Zn, that we want to count the degrees of vertices. We want to count the number of edges, that is the structural properties. Now, suppose you consider that n is a product of this p1 to the power n1, p2 to the power n2 up to pm to the power nm. Then the first question is how many vertices are there? Naturally, all the, Zn is PID, all these are principal ideal domains. So, principal ideal ring. These are principal ideal ring, and so all the ideals are principal ideals, and these ideals are generated by the non-trivial factors of n, that is accepting 1 and n. So that is why you see the counting has -2 in the last line. And the other part, the total number of factors of the number is very well known to you. That's the combinatorial all well known formula. That is the number of factors of p1 to the power n1, p2 to the power n2, ppm to the power nm. That is n1 plus 1 into n2 plus 1 up to nm plus 1. -2 is for 1 and n. And these are standing for the whole ring and the zero ideal. So the total number of vertex is the last line, that is the formula is showing the total number of vertices of the graph. Now we will count the degrees of the vertices. So suppose we consider an ideal that is of the form that is p1 to the power n1, p2 to the power n2 up to k to the power nk. And then the other part you see that is the not full nk plus 1 up to nm. These all ij's that you see in the third line, 0 less than equal to ij less than nj. And so this is a particular general idea. And in the case k equal to 0, we say that not all ij's are 0, because otherwise it becomes the 0 whole ring, because it becomes 1 while powers are 0. Now, how many ideals are adjacent to this particular ideal? Naturally, whose LCM with this will be n. Those are not adjacent. And the graph itself and the ideal itself is not adjacent to itself, because we are considering the simple graph. So the ideal that contains the factors like this, so that the LCM contains the full n. So the ideal must contain the factor. You see that in the 2 lines below the violet line, that is the vi must contain, which is ideal, which is not adjacent to vi, must contain the factor pk plus 1 to the power nk plus 1 up to pm nm. Now, how many of them? So again, the same kind of counting. So this part is fixed. So only part we can vary 0 to n1, 0 to n2 up to 0 to nk. So total number is n1 plus 1, nk plus 1. And the -1 is coming when all of them are just reaching the full value, that is n1, n2 up to nk, then it is the 0 ideal. So this number and the vertex is not adjacent to itself. So this -1 will be added the +1. So you see that total number of vertices which are not adjacent to that particular ideal is n1 + 1 into n2 + 1 up to nk + 1. And if k equal to 0, that is all of them are not in the full power, that is the P1 to Pk is suppose absent, so all these powers are less than the highest power, the prime power that is present in n, then only the ideal itself is not adjacent, all other vertices are adjacent to it. So these are the degrees of vertices. So the degrees of vertices is naturally number of vertex minus the ni, so you get that degree is t minus ni, where t is the number of vertices. So in this way, you can count all the degrees of vertices of Zn. For example, for Z36, you see first how many vertices are there. So you see that this is 2 square into 3 square. So total number of factors are 2 + 1 into 2 + 1. And that -2 because to get that 1 and 36. So there is 3 into 3, 9 minus 2, 7. There are 7 vertices, and those are present here, written here. You see 2, 3, 2 square, 3 square, 2 into 3, 2 square, 3, 2 into 3 square. So these are all the vertices, 7 vertices are there. So particularly, suppose we want to know that what is the degree of 2 square 3, and then that is 12. So if you get that any ideal Z that is not adjacent to this, that must contain 3 square, so as the LCM becomes 36. So 3 square containing ideal, you see that 3 square containing ideal is only, there are 2 ideals which are 3 square containing ideal, right? So number of vertices, here you see that not adjacent to these 2 and the ideal itself, that is 1. So 3 vertices are not adjacent. There were 7 vertices. So 4 other vertices are adjacent to this ideal. So the degree of this ideal 12 in the ring Z36, its degree is 4. So in this way, you can calculate easily the degree. But in the other way, that if you consider the ideal k as that's generated by 2, you see that excepting k, all others are adjacent to this vertex. So its degree is just 7 minus 1, that is 6. Let me see whether the figure is here. Yeah, the figure is here. You see that for the 12, there are 4 adjacent vertices, 2, 3, 6, and 4. Its degree is 4. And for the vertex 2, you see that its degree is 6. All other 6 vertices are adjacent to it, so its degree is 6. So this is the calculation of the degrees. And here there is another example for the graph which is comparatively bigger, the number 360. And here you see the powers are 3, 2, and 1. So the total number of vertices is 3 + 1 into 2 + 1 into 1 + 1 minus 2, that is 22. And so you see that suppose we want to find out the degree of the ideal generated by 24, that is 2 cube 3. And now, so we know that we require 3 square into 5 in that ideal, which is not adjacent to it. So how many ideals are like this that you can count? That ultimately you can count there are 3 such ideals which contains 3 square into 5, because the other part is 2 cube. So you can have that, you can have only that 1, 2, and 2 square. If you have 2 cube, then the total becomes the 0 ideal, 2 cube 3 square 5. So only you are getting 3 vertices, that is 1 into 3 square into 5, 2 into 3 square into 5, and 2 square into 3 square into 5. So there are 3 vertices plus 1 itself, which are not adjacent. So 4 are not adjacent. So its degree is 22 minus 4, total there were 22 vertices. 4 vertices are not adjacent, so its degree is 18. And in the similar way, if we want to count that the vertex with 2 into 3, that is 6, and all vertices are adjacent to it except itself, so its degree is 21. Let me surprise you by showing the figure of 360. You see how complicated, how dense, or it's not complicated, I should use the term dense. You see that only it is 360 and how dense this graph is. The circles that are shown, that is instead of the vertices, which are adjacent to in between themselves and which are adjacent to all the edges that is ending at that point. So otherwise we could not draw the graph, and we are just showing the graph in this way. And here you can see that what we were searching, 24, first 24, it's 18. So you may count here that there are 18 edges from 24. Actually, you can see not 18 lines here, because the first, the rightmost line you see, go to the first point that contains 2 elements, 20 and 60. So that you have to count 2. For example, the from the rightmost to the third one, you can have the third is consisting of, over the top, you see the point 2, 3, 6. So you have to count 3 in this way. So in this way, you can count totally 18. And where is 6? 6 in the top. And that you see that it is adjacent to all the vertices excepting itself. So this is the graph of Z360. Now, by this degree counting, we can move to the some properties. Oh, this is a summary of the degree counting, that suppose n is belonging to m. M here throughout this talk, we consider m here is a number, say set of numbers which are greater than 1 and not prime. Because for primes and 1, we cannot get that non-trivial non-zero proper ideal. So we get that n belongs to m, that means the vertex set is void, no, non-void. However, suppose n is this expression that p1 to the power n1 up to pm to the power nm, then total number of vertices is tn, that is given as this formula written in the magenta color. And then you see that the second and the third magenta color line, that is the degree of the ideal that is generated by I, that is given in the first line below the first magenta line, that is p1 to the power n1 to pk to the power nk, then pk plus 1 to the power ik plus 1, and so on. So this degree is this one. And if k is non-zero, and if k is 0, then degree is simply t minus 1, and so this tn minus 1, the degree, that is the product of all of them, minus 3, that is the degree. So this is the degree formula. And from this, you can compute also that number of vertices of a fixed degree, that how many vertices, if I give you some number, then if I ask you that how many vertices are there of that degree, and that can be also done by some fighting with some combinatorics, you can get that how many vertices are of that fixed degree. The highest degree that you can have, that n1, n2, nm minus 1, and there are t minus 1, that is the degree is t minus 1. And the number of vertices, sorry, the degree is t minus 1. The number of vertices is n1, n2, nm minus 1. These are the number of vertices of the highest degree. And all other vertices, the number of vertices of possible degrees are just t minus of these expressions, some nr1 plus 1, nr2 plus 1, and so on. And that is the number, is the product of nr, where r is not belonging to one of the r1 or 2 rs, but it is belonging to this ri 1 to m. So in this way, you can, this is a complicated combinatorial proof is there. But however, it is possible to count the number of vertices of a fixed degree of the Zn. Now, shortly, we go for the Turing properties, that is Eulerian and Hamiltonian properties. And because now we know that the degrees of the vertices of the graph, and we have that sum of the degrees of the vertices of the graph, we know that is equal to the twice the number of edges. So you can count the number of edges of the graph. Oh, sorry, before Eulerian property, you can count the number of edges of the graph easily, because you have that sum of the total degree is equal to the twice the number of edges. And if we calculate, the formula is very typical. You see that written in the middle in the magenta color, that is in the theorem, that is half of 1 plus tn square minus tn square. That is the number of vertices of the graph Zn square. Actually, that is the very simple form of the expression. There is a long expression, and if you simplify and simplify and simplify, and then ultimately you get that nice formula for calculating the number of edges of the graph. So in this way, you can count the number of edges. And for example, suppose you consider the graph P square QR. Now the total number of vertices is 2 plus 1, 1 plus 1, 1 plus 1 minus 2, that is 10. 3 into 2 into 2, that is 12, minus 2 is 10. And Tn square, that is if you square n, then it is P4 Q square R square. So total number of factors 4 plus 1, 2 plus 1, 2 plus 1, and that minus 2. So you see that 5 into 3 into 3. So 5 into 15, so 3 15s are 45, minus 2, that is 43. So the total number of edges is half of 1 plus 10 square minus 43. And that you can compute that it is 34. So there are 34 edges in any graph of P square QR, where P and PQR are distinct primes. So in this way, you can calculate the number of edges in the graph by not drawing the graph exactly. Then the Eulerian and Hamiltonian property we want to discuss. You see that it is in the, if you want the Eulerian property, this well-known theorem due to Euler, that the graph is Eulerian if and only if every vertex is of even degree. This is the result for connected graph, and in general we say that there is only one non-trivial component, and other vertices may be isolated, and the graph every vertex degree is even. Those who are new to the graph theory, I am just saying that a graph is Eulerian if you can make a tour of the graph, that starting from a vertex and visiting all the edges of the graph, that is traversing all the edges of the graph, but only once. You cannot repeat the traversing edges of the graph. If you can come to the same vertex, and then this is called an Eulerian circuit of the graph. There is no responsibility of visiting all the vertices. You have the responsibility of visiting all the edges only of the graph. Then it is called the, or you can repeat also the visiting vertex, but you cannot repeat the edges. These graphs are called, the graphs having the Eulerian circuit are called Eulerian. And a connected graph is Eulerian if and only if it is an even graph, that is every vertex is of even degree. Now in our particular cases, here we have seen that the graph of Zn is Eulerian, either it's a product of distinct primes or it is the product of prime powers where every power is even. So these are the two types of Eulerian graphs, and only possible two types of Eulerian graphs that can be formed for the graphs of Zn. For example, you see that if you have that n equal to 30, that is 3 distinct primes, and you see the graph becomes Eulerian the Z30 has 6 vertices because 1 plus 1 plus 1, 2 into 2 into 2 minus 2, that is 6. And 6 vertices are 2, 3, 5, 6, 10, and 15. And you see that this is whether the picture is here. However, first I describe you the results and then I show you the picture. Suppose I is the ideal generated by 2. So here you see Ni is 1 plus 1, 2. So the Gi, that is its degree, is T minus Ni. So when it is 2, the requirement is that the ideal that is non-adjacent must contain 3 and 5. And so the ideal that is only ideal, that is 1 into 3 into 5, because 2 into 3 into 5 is n, that is the 0 ideal. So only 1 and it is itself. Those are non-adjacent here. So total number of vertex was 6, so the degree is 4. And similarly, you can have that degree of 3 and degree of 5 is also 4. But in the case of degree of 2 into 3, you see that you require that must contain 5. So there are, you can have that 2 other vertices are there, that you say that 4 vertices you can have that these are non-adjacent. So you have that 4 vertices are non-adjacent, so their degree is 2, 6 minus 4. So degree of 3 into 5 is 2 and degree of 2 into 5 is 2. And so all the vertices are of even degree. Degree of 2 into 3, 2 into 5, 3 into 5, these are of degree 2. And 2, 3, 5, these are of degree 4. So all the vertices are of even degree. And so the graph is Eulerian. Let me show you the picture. It was in the first slide. Yeah. This is basically the graph of PQR, and you see there is, you can easily make an Eulerian tour. Suppose you start from PQ, you go from up to P, then PR, then R, then visit again P, and then Q, then R, then QR, Q, and again PQ. So in this way, in this way, you can visit all the edges, but only once, and you can make an Eulerian tour here. And so the whole graph becomes Eulerian, and here you see that the graph is connected and all the vertices are of even degree. These 3 vertices are of 2 degree and 3 vertices are of degree 4. Right. So you have that Eulerian case, but in the case of graph Z12, you see that total number of vertices is Z2, 2 plus 1 into 1 plus 1 minus 2, that is 4. So 3 into 2, 6 minus 2, that is 4. So there are 4 vertices, namely 2, 3, 2 square, and 2 into 3. So you see that the non-adjacent vertices of the 2 is only 1, that is itself. And non-adjacent vertices of 2 square, that must contain 3, and so there is only 1 and 2 are there. So 2 and plus 1 itself, that is 3. So 3 are non-adjacent. But total there are 4 vertices, so its degree is 1. And degree of 3 and 2 into 3, you can prove that there's 2. So the degree sequences, you have that degree sequences are 3, 2, 2, 1. So there are 2 odd degree vertices, so the graph cannot be Eulerian. And you can remember this Z12 graph, there is a triangle and one antenna-like thing over there. So, and that is not Eulerian, and you cannot get an Eulerian tour from here, because whenever you start, if we start from the, say, upper point, Okay, I may go to the graph. This was in the beginning. Okay, let me. Oh, this is not working here also. Only I can scroll. Yeah. So you see that if you start from 2, so up, if you go to 4, so there is no way of coming to 2 back, because then you have to repeat the edge. And if you traverse 3 and 6 and come again 2, so you can go to 4, but you cannot end at 2. So there is no Eulerian circuit is possible, and therefore the graph is not Eulerian. And in fact, you see that 2 and 4 are of odd degree, but 3 and 6 are of even degree. So the graph is not Eulerian at all. Oh, sorry. I have searched for a long, it was the next slide. So you see that graph is not Eulerian, but it is in another context, the graph is not Hamiltonian also. Now, what is a Hamiltonian graph? Again, who are new to graph theory, I am just making you reminder, the graph is Hamiltonian. Here the tour is like that. You have to start from a vertex. You have to come again to the vertex, but without repeating any vertices. You have to come back to the same vertex, but without repeating the vertices, then the graph is called. This cycle is called a cycle. This is called a spanning cycle or Hamiltonian cycle. And this graph is called Hamiltonian if such a cycle exists in the graph. And you know that Hamiltonian problem is still unsolved, that there is no necessary and sufficient condition for determining whether a graph is Hamiltonian or not. There are some necessary conditions, there are some sufficient conditions, but there is no necessary and sufficient condition. But Eulerian problem is solved. Euler itself solved it, that it is Eulerian if and only it has at most one non-trivial component and all the vertices are of even degree. But Hamiltonian problem is still unsolved. And one very famous algorithm, that is traveling salesman problem, that is also unsolved here. That cannot be done in polynomial time. And so the major problem of the theoretical computer science computations are, one of the major problem is this Hamiltonian problem, and that cannot be done for large n. Even in your computer, if you try to search for such a Hamiltonian cycle even for the graph of more than say 30-40 vertices, so it is nearly impossible in many cases to determine whether the graph is Hamiltonian or not. However, here also graph is not Hamiltonian. You see that wherever you start with a vertex, you have to come back to the same vertex by visiting all the vertices but once. But here, if you start from 4, then go to 2, 3, 6, and then unless you repeat 2, you cannot come back to 4. And so the graph is not Hamiltonian. Similarly, if you start from 2 or 3, you cannot visit all the vertices and come back to the same point without repeating the vertex. Say from 3, so you can go to 6 to 4, but you cannot come back to 3. From 2, 2, 3, you can come back to 2, but you can never reach 4 again by coming back to 2 without repeating the vertex. So in this way, this is the Hamiltonian problem. And so now we search for which graph of Zn is Hamiltonian. And you see that here this graph is not Hamiltonian, but here for Z30, you see the graph is Hamiltonian, and a Hamiltonian cycle is shown by the dotted line, 2 to 6, 6 to 3, 3 to 15, 15 to 5, 5 to 10, 10 to 2. So that is a Hamiltonian cycle that you can have, that is also called the spanning cycle. This graph is Hamiltonian. So the question is that for which n the graphs are Hamiltonian and which n the graphs are not Hamiltonian. So after a long study, we came to get some lemma that which says that if n has the expression of p1 to the power n1, p to the power n2 up to pk to the power nk, and then the graph of Zn is Hamiltonian, first we get some sufficient condition that Hamiltonian if the product of this ni plus 1 is greater than or equal to 5, or the product of n1 into nk minus 1 is greater than or equal to k. Then we got the graphs are Hamiltonian, and then we proved that any multiple of any, if Z alpha is Hamiltonian, and if we get a prime multiple of alpha, and that can be proved to be Hamiltonian. And that is a very fine and nice result, because that gives you again some extension like that. I told you that R to Rx result. This is some extension kind of result, that you have that this graph of Z alpha is Hamiltonian, then you have that some prime times of alpha, where that prime doesn't divide alpha, that's not a factor of alpha, that is also Hamiltonian. But then with all these lemmas and other results, ultimately we can conclude that the graph of Zn is Hamiltonian except n is one of the following form: p square pq, p square q pq. So you see these are very trivial graphs. P square is a single vertex graph. PQ is two isolated vertex graph, and P square Q is just, I have shown you that the graph of 12, and PQ is just an edge, P and P square, the two vertex just K2 complete graph. So you can say almost all graphs are Hamiltonian of Z. So again, you see the graph is dense, almost all graphs are non-planar, almost all graphs are Hamiltonian. And so that says that the graph is dense. There are a lot of edges of these graphs. We are coming into the mostly concluding part. But before coming to the concluding part, I'm asking you, you can ask me some question, and then I will tell about something very surprising and very nice to hear. But before that, if you have any question, you can ask me now also.
So these results are stated for Zn, but are there extensions to other rings? Like, for example, I believe principal ideal rings, these results will hold.
Yeah, actually, in our initial and beginning paper, have you seen that we discussed that we got some results for arbitrary rings for connectedness and completeness. But then this counting and onwards, we concentrated on Zn. But after that, hundreds of papers of these intersection graphs of ideals of rings have been published. And you see that, and that I mentioned, I will also give you the reference, that a very good survey paper that is written by Dr. I.B. Chakraborty and Father Professor Joseph Varghese of Christ University. And they have considered almost all the results of the intersection graphs of ideals of rings. And I will show you the paper also just after this 1 point thing that I want to tell you. And there I will show you that lot of results, lot of extensions, and for arbitrary rings, lot of variations of these graphs are done. This was the result was just the beginning. This result I am talking just was the beginning of the story, and then the for the last 12 years. So there are a lot of waters flown in the river, and so as you can see that the citation is nearly now more than 200. So more than few hundreds of papers have been studied in that, because this is very catchy, like these things, because the ring theory, and one can be provoked to the extension, as you can, as you stated, that immediately you want to generalize it for principal ideal rings and some principal ideal domains in particular. So yes, there are many extensions are there. Not all these things I am describing today. I am giving references, and I will discuss I will show you some glimpse of some results of it.
Okay, thanks.
Okay, so since the thing is there, so I can go to there. Just for going to the survey paper, before going to survey paper, I just want to give you a surprise. Is that actually we have started with a result of this talk that every graph, every simple undirected graph is an intersection graph. But here you see that not all the graphs are intersection graphs of ideals of rings, because you see that our graph is very dense, that which graphs are very sparse, those are not here. But one interesting result is that every simple undirected graph is an induced subgraph of some intersection graphs of ideals of rings. Actually, one graph, it may not be the intersection graphs of ideals of rings, but it is an induced subgraph of some graphs of some mother graph, you say, of intersection graphs of ideals of rings. And that is how that I am showing you schematically that suppose, so it is better that we discuss. Oh, sorry, here it is another part counting non-isomorphic graphs. Okay, I am coming into that. But what I was saying, better yeah, there was a part I missed that. So this result is saying that every simple undirected graph is a reduced subgraph of the graph of Zn. And you see that how you can construct them. What you have to do, you have to first collect, like that group you can remember, to collect all the maximal clicks of the graph. So here also you can collect first all the maximal clicks of the graph, and you assign distinct prime numbers for the maximal clicks. And then you label each vertex the product of primes that in which clicks it is belonging to. And then you relabel the vertices by making them distinct by using different powers of the primes. And finally, if you get the number n, that is the least common multiple of all of them. And then if you divide each of this level, that is, if you divide n by each of these level, that you can get the final level. That it is better understood by a figure or an example. You see, there are two maximal clicks here. One is formed by V1, V2, V3, V4. This is K4, and another is forming K5 except V1. So I am assigning each of them P and Q, each of this click. And the number I am writing in the step 2, the vertex V1, it is belonging to the click 1, but not click 2. And so I am assigning P. But V2, V3, V4, they are belonging to both the clicks. So I am assigning PQ. V5 and V6 are belonging to only second click. So I am assigning Q. So then I am making distinction by making distinct powers. That is P square Q and PQ square for the third and fourth vertices, and Q square for the sixth vertex. And then you see the LCM is P square Q square. So I divide n by the step 3 level. And that will give you PQ square, PQ, Q, P, P square, Q, P square. Now you can verify that if you get the graph of Zn where n is P square, Q square, so your given graph is the induced subgraph of these 6 vertices of the mother graph Zn. So from this you can also understand that if you think that considering the graphs of Zn only, the intersection graphs of ideals is not so wide, but this particular result says that actually the graphs of Zn is a very broad and wide class of graphs for the intersection graphs of ideals of rings, because it gives you every simple undirected graph in a subgraph representation of these intersection graphs of ideals of Zn. And that is actually very important in the context of isomorphism problem, graph isomorphism problem. You know that one of the most famous or infamous problem in graph theory is the graph isomorphism problem, where we want to get either some coding or some unique way to get a representation of a graph where we can uniquely represent a graph so that we can decide whether two given graphs are isomorphic or not. And those who are not so much conversant in this area, I can tell you one more interesting thing, that there are two major problems in the, you say that in mathematics or in combinatorics, you can say, or in computation or computer computation, that getting the prime factorization of a natural number in log n time, and the graph deciding whether two graphs are isomorphic in the order of time of their input vertices, number of input vertices. So, or any polynomial of that. So these two problems are, it is not known whether for these two problems, whether there exists any polynomial time algorithm. Polynomial time algorithm means if you give input n, so if the number of computation, I am saying very naive and rough language, so that everybody can understand. So if the number of steps of the computations of the order n square, n cube, n4, even it may n to the power 1000, but 1000 is fixed. Then you say it's a polynomial of n, then it is the class of algorithm which can be solved polynomial times. But there are NP complete algorithms, which is called non-deterministic polynomial time algorithm, like Hamiltonian problem and many others. But these two problems, the isomorphism problem, factorization problems, are still to be proved to be NP complete, and also still to be get any polynomial time algorithm for them. So they are two still mysterious problems, and so one do not know that whether there is a polynomial time algorithm will come in future for graph isomorphism problem or not. So people are trying in various ways to get some unique form of representation of graphs. So here you can have some various ways of looking at the graphs. So here you can have some way of representation of graphs, and I don't know whether in future some can derive some coding from the structure of the mother graph of the intersection graphs of ideals of Zn, because every intersection, every simple unedited graph is an induced subgraph of it. However, this is just a hope. I do not know that this hope will see the light in future or not. So the last thing actually should be the last but one, but in the last thing I am telling that how to count the non-isomorphic graphs of Zn. That is in the context is very important, that I am saying you that which graphs of Zn are isomorphic and which graphs of Zn are not isomorphic, and to count the number of non-isomorphic graphs are very much important. For example, here, suppose we take 4. So suppose we want to know that how many intersection graphs of ideals of rings are of vertex 4. So you see that you can remember the total number of vertices was that factor minus 2. So if you take the plus 2, then it is 6. So it is amount to say that in how many ways you can factor 6. And it is only 2 ways you can factor 6 itself, and 3 into 2. So you can have only 2 non-isomorphic graphs of vertex 4. Either it is form of p square q. How you come p square? Is square 2 you came from 3 minus 1. And that q to the power 1 is come from 2 minus 1. So you can remember the product was n1 plus 1, n2 plus 1, and so on. So it is 3 minus 1 and 2 minus 1. So the graph is of the p square q form. Or it is 6, so 6 minus 1 is 5. So it is either of the form z p to the power 5. So there are only 2 such graphs are possible of vertices 4. And that is explained here with degrees and so on. And there, if we count degrees, you have that P5 is a complete graph. So all of them of degree 3, it is a graph complete K4. So all of them are of degree 3. But here, P square Q is the graph that is the graph of 12. You can remember triangle and an antenna with over it. There is a vertex of degree 1, 1 vertex of degree 3, and 2 vertex of degree 2. So certainly these 2 graphs are non-isomorphic. And these are the only non-isomorphic graph of vertex 4 among the intersection graphs of ideals of Zn. These are these two graphs of Z p square Q and Z p to the power 5. Now, so our theory goes like that. Suppose we want to know that how many graphs of P vertices are non-isomorphic. So we make it T plus 2. So we get that this, we have to factor them. And if we can factor them M1, M2, M nu, then if you have that, this is a graph of Zn will be where n is P1 to the power M minus 1, P2 to the power M2 minus 1, and so on. So the whole thing becomes the number of unordered factorization of T plus 2. We say that it is an unordered factorization where we do not distinguish between 2 into 3 and 3 into 2. So if we give a natural number and we ask that how many unordered factorizations of n is there, that is called the symbolized by P star n. You can remember the number of partition of n, that is the unordered addition partition of n. That in suppose 3, you can write 3, 1 plus 2, 1 plus 1 plus 1. There are 3 partitions of n. But it is multiplicative partition. It is how many ways you can factorize n. So this number, if we want to calculate, then this is the number of non-isomorphic graphs of Zn as the number of unordered factorizations of T plus 2, where T is the number of vertices for which you are searching with. So the whole thing that you have to find the number of unordered factorizations of T plus 2. And when we got this problem, we tried to solve this problem to find this thing. I am not going very much details on it. There are some formulas I am showing you, that there are some recurrence relation formula that we can derive like this, that will give you the number of unordered factorization in terms of non-unordered factorization of some factors. There are 2 simplified form of this also, that P star n P is sum of P star of D, where D divides n. And in particular for P q to the power n, it is sum of Pi, where Pi is the additive partition number. So these are some simplified form. By these forms, And in general, this recurrence formula, you can derive the number of unordered factorizations. But before that, I am showing you an example that suppose you take a large number that is comparatively large, that is 10. So you have 12. Now 12 has 4 such factorizations. You see 12, 2.2 into 6, 3 into 4, 2 into 2 into 3. So there are 4 non-isomorphic graphs of 10 vertices, which are intersection graphs of ideals of Zn. And for 12, it is the P11. For 2 into 6, it is P into Q to the power 5. P comes from P to the power 1, comes from 2 minus 1. And Q to the power 5 comes from 6 minus 1. Similarly, it is P square QQ and PQR square. And these are the 4 possible 10 vertices intersection graphs of ideals of Zn. And you see that these graphs are non-isomorphic. This is the complete graph, that is P11. And this is the graph of PQ to the power 5. This is the graph of P square QQ. And this is the graph of PQR square. It is comparatively less density than these graphs. So here is some calculation for further large number 70. So you can calculate this by this recurrence relation that how many non-isomorphic graphs of 70, but then that is the how many unordered factorizations of 72. And that after many calculation, you can have that the number is 16. There are 16 factorizations of 72. So there are 16 non-isomorphic graphs of 70 vertices. So yeah, so that is the last. That is the end of this talk. And we can have the reference. And in the third reference, you see that is the initial paper of 2009. And after that, in the 12 years, there are a lot of papers, hundreds of papers of over the intersection graphs of ideals of rings. And this is the survey paper in the number 4 that I told you. And this is the second is the paper of Bozak, that is the initial paper of algebraic graph theory of starting of the theory of graphs from groups or semi-groups. And then this is the Cezanne-Polak paper in the first. And these are the other references. This is the last paper, is the paper of Zelinka. I don't know if possible, then I could show you the reference paper, but here whether it is open or not, that is difficult. I don't know how to get rid of this. Okay. So I am stopped this sharing.
Yeah. So thanks. So are there any questions? Participants, if you have any questions, please ask. Okay, so so I think they can look at the survey, like you mentioned in your talk. They can look at this survey paper by Chakravarti and
so
Joseph Verghese.
I'm trying in the document if I can show you. Yeah, that is this
Okay.
one.
Yeah.
This one you can see that is the survey paper. It is just online preprint.
Okay.
The volume number is it's just recent. They have published it, and so you see that there is. Let me then show you. So probably in the a later part, you see this is the Hamiltonian property. Yeah, you see that, for example, it is the independence number, the domination numbers. These are now also, and you see that these are for commutative ring with identity. Even they are searching for the perfectness of this. So the coloring of the graphs, you see that there are results of click numbers and chromatic numbers of the graphs. So a lot of works has been, here you see that there are various kinds of rings that is considered and for which these click numbers, chromatic numbers are studied. In fact, if you go to the reference section, yeah, then you see that there are 111 references are there.
Okay.
And from these references, you'll see that people have studied a lot. One way from graph theory point of view, another way from ring theory point of view. So this is a big study.
Yeah.
And I invite all the young persons and young researchers that this particular survey paper will help you to know that which results are done already, and you can carry over some other results. Here some open problems are also given here. So you see that that will help you to study these graphs. Thank you.
Okay. Yeah. Okay. So yeah, if there are no further questions, so it's a pleasure to thank Professor Shamik Ghosh for this talk on intersection graphs of ideals of rings. I think some of the participants, they can take up this topic for their research, further research. So thank you, Professor Ghosh, for accepting our invitation and for being here in this conference and giving a talk. So I'm sure later on when things start offline, we will have a chance to meet in the offline setting. So thank you very much.
Yeah, you can communicate by mail also.
Yeah.
Shamik.Ghosh, JadavpurUniversity.in. That is
Right.
the
Yes.
address.
We have your email ID.
Easiest way to remember. I have other email, but it is
Okay.
easiest way to remember. Shamik.Ghosh, JadavpurUniversity.in.
Okay. Okay.
So and you can copy or take screenshot of this
Sure.
reference of the survey paper also. So this will help you to for further research. That is our actually motto of this workshop, to lead further research from this some area to other. Thank you.
All right. Okay. Thank you.